everyone. In this video, we're going to look at the derivatives of exponential and logarithmic functions. Okay, so let's start with exponential functions. And we're going to start with the derivative of e to the x, which actually equals e to the x. I always say this is the easiest rule of all to remember because derivative of e to the x equals e to the x. Nothing changes. But let me show you where this derivative actually comes from. To find the derivative of e to the x, we actually go back to our definition of the derivative, which, if you recall, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And so if we apply this rule to e to the x, we'll get the limit as h approaches 0 of e to the x plus h power minus e to the x all over h. Okay, now, in order to evaluate this limit, one thing that we can do is we can rewrite the e to the x plus h as e to the x times e to the h power. And this is just using properties of exponents. You usually learn it something like if you're multiplying powers of the same base, you add your exponents. And so we're just starting with this and working backwards. Okay, so e to the x plus h can be rewritten as e to the x times e to the h. Okay, then minus e to the x, okay, all over h. All right, then what we can do is we can actually factor out an e to the x in the numerator. So we'll end up with e to the x times e to the h minus 1 all over h. And because we're evaluating the limit as h approaches 0, this e to the x, which is not in terms of h, is a constant multiple, so we can actually move it in front of the limit. Okay, so now we'll have e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. Okay, now the limit of e to the h minus 1 all over h as h approaches 0, we can actually evaluate that limit graphically. And so on the next slide, I actually have the graph of e to the h minus 1 all over h. And so if we evaluate the limit as h approaches 0, you'll see as x is approaching 0 from both directions, y is approaching 1. So this limit equals 1. And so that means we can go back to the previous slide. If I can get there we go. And this will just end up being e to the x times 1, since that limit we know equals 1, and so that's just going to equal e to the x. Okay, so that's how we get our new derivative rule, that the derivative of e to the x is e to the x. Okay, now you just need to remember that rule. I was just showing you where it comes from, and it just comes from definition of the derivative. Okay, so let's look at some examples. Now, in our first example, we have y equals 2 times e to the x. So this one is pretty easy because 2 is a constant multiple. So when we find the derivative, we would just bring the constant multiple down and multiply it times the derivative of e to the x, which is e to the x. So actually nothing changes. The derivative of 2 times e to the x is still 2 times e to the x. Okay, now look at our next example. We have y equals e to the 4x power. Okay, now notice x has been replaced with 4x. So that means you have to use chain rule, because this is now a composition. Okay, so it'll work like this. dy dx would equal, okay, the derivative of the outside, which would be e to the x, is still going to be e, okay, to the x, but I'm just going to put parentheses there, because inside the parentheses, we're going to keep the inside the same, but then multiply by the derivative of the inside. Derivative of 4x is 4. Okay, so then, just to simplify this, we probably just move the 4 in front of the e to the 4x, and you can just write it as 4 times e to the 4x power. Okay, but the emphasis there is on the chain rule. Okay, so if your exponent is more than x, you got to substitute in place of x and then multiply by the derivative. Okay, using chain rule. Okay, a couple more examples where I want to show you that we could still maybe use product or quotient rule with e to the x. And so the example on the left, y equals x squared times e to the x. This would be a product rule because we're multiplying two functions. So our first function is x squared, and our second function is e to the x. And so dy dx would equal first, which is x squared, times derivative of the second. Derivative of e to the x is still e to the x, plus second, which is e to the x, times derivative of the first. Derivative of x squared is 2x. And then, as far as simplifying goes, I mean, honestly, you could probably drop these parentheses and just write it as x squared e to the x plus, now I might just switch the order here, so I can get rid of those parentheses, so 2x e to the x. And then, you know, because factored form is simplified form, you know, we might just factor here. Looking at each term, we can factor out an x, and we can factor out an e to the x. And so from this term, the only thing left is an x. And then from this term, the only thing left is 2. So we get x e to the x times x plus 2. Okay, so think about factoring in order to simplify. Okay, next example, we've got 2 e to the x divided by e to the x plus 1. So this derivative would require quotient rule. Okay, and so remember, we're just going to think of this as the high function and the low function. And so dy dx would equal low, which is e to the x plus 1, d high, which is the derivative of the numerator, but that derivative doesn't change anything. It's still 2 e to the x, minus high, which is 2 e to the x, times derivative of the bottom function. Derivative of e to the x is e to the x. Derivative of 1 is 0. So we're done. Okay, all over low squared. Okay, and then as far as simplifying goes, again, I would look at maybe factoring that numerator. We could definitely, to get rid of some parentheses, like distribute the 2e to the x. Okay, now you guys, when you multiply e to the x times e to the x, this is where you're going to add your exponent. So it'll become e to the x plus x, which will equal e to the 2x. Okay, I just wanted to emphasize that. Okay, so 2e to the x times e to the x will become 2e to the 2x. Okay, plus 2e to the x minus 2e to the 2x. Okay, all over e to the x plus 1 squared. It looks like we could, yeah, I think I would just maybe, well, actually, no, I'm sorry, we can do some simplifying. We've got 2e to the 2x minus 2e to the 2x. Those are going to cancel out. Okay, so that was kind of nice. So we'll get 2 times e to the x over e to the x plus 1 squared. There we go. Okay. Moving on. Let's now look at the derivatives of logarithmic functions. And I just want to remind you that a logarithmic function is the inverse of an exponential function. So natural log of x is the inverse of e to the x, okay? And the derivative of natural log of x actually equals 1 over x, okay, comma 4x greater than 0. Now, why do we need this? Because the domain for natural log of x is greater than 0, okay? You cannot plug in 0 into a logarithm, nor can you plug in a negative number into a logarithm, okay? If you guys remember, the graph of natural log of x actually looks like this, and so you can see there's actually a VA, you know, that your domain would be x is greater than 0, okay? So that's why we have to just stipulate that because of the domain for the function natural log of x. Okay, but anyway, the new rule you have to remember is that the derivative of natural log of x equals 1 over x. Now again, let me show you where that comes from, okay? All right, so let's just say we let f of x equal e to the x. So knowing that natural log of x, you know, is the inverse, I'm going to let g of x equal natural log of x, okay? All right, so remember this rule. If f and g are inverse functions, then g prime of x equals 1 over f prime of g of x. That's the rule for the derivative of an inverse function. Okay? So in this case, g prime of x would be the derivative of natural log of x. Okay? Now, since g equals natural log of x, in this rule, we're just going to replace g of x with natural log of x. We can do that because they're equal. Okay, now we can find the derivative of f, because you know that rule now. So if f of x equals e to the x, then f prime of x equals e to the x. And so this rule is now going to become 1 over e to the natural log of x. And e to the natural log of x, they undo each other, and that all just simplifies to equal x. And so you end up with just 1 over x. Okay, so anyway, that's where the rule comes from. The main thing you need to remember is this new rule, that derivative of natural log of x equals 1 over x. Okay, let's look at some examples. All right, so we want to find the derivative of these functions. Our first function is natural log of 4x. Okay, now if that was just natural log of x, then it would just equal 1 over x. But because the x has been replaced with 4x, we have to use chain rule. Okay, so dy dx would equal, so here's what you do. It's going to be 1 over, we're going to replace the x with 4x, but then times the derivative of 4x, which equals 4. So here, the 4's are actually going to cross reduce, and you're actually just going to end up with 1 over x anyway. But I wanted to show you the right way to get there. It's technically 1 over 4x times 4. Okay? All right. Here, for our next example, we're finding the derivative of natural log of 3x squared minus 5x plus 8. Okay, so here's how I would start it out. The derivative is going to be 1 over, okay, what's in parentheses, but then times the derivative of the inside. And so that derivative is going to be 6x minus 5. Multiply straight across, and we get 6x minus 5 over 3x squared minus 5x plus 8. And again, this was also using the chain rule. Okay, let's look at a couple more examples. Okay, so here we've got y equals x squared times natural log of x. So we have to do product rule. Okay, so our first function is x squared. Our second function is natural log of x. So our derivative is going to be first times derivative of the second. Now we know derivative of natural log of x is 1 over x. Plus second times derivative of the first. And then this will simplify a little bit because x squared times 1 over x, this will all just simplify to equal x. And then honestly, just so I can drop the parentheses, I'm going to switch the order here and just make it 2x times natural log of x. And then if you write it like that, you can get rid of all the parentheses. We could maybe factor out an x. I'm noticing, so sometimes you might see the answer written in factored form, possibly like on a multiple choice question. Okay, in this next example, the function is natural log of x divided by x. Okay, so we got to do quotient rule here. Okay, so dy dx is going to equal, okay, remember the high and low. So it's going to be low d high minus high d low all over low squared. Okay, and then as far as simplifying goes, x times 1 over x, that just equals 1. So our numerator just becomes 1 minus natural log of x, okay, all over x squared. And that's pretty much all we can do there. Okay, so you guys, in this next few examples, I wanted to show you that we could also use properties of logarithms that actually will make finding some of these derivatives easier. Okay. Now these are these are the three properties of logarithms that I'm referring to. If we have log a times b, we can expand it into log of a plus log of b. If we have log of a divided by b, we can expand it into log of a minus log of b. And then if we have log of a raised to the b power, remember we can move the b down in front, and it will equal b times log of a. Okay, so first of all, in example 13, anytime you have a radical, no matter what rule you're using to find the derivative, always convert it to a fractional exponent. Okay, so the first thing I have to do here is rewrite this as y equals natural log of x squared plus 2x minus 3 raised to the 1/2 power. And so now we can actually use property number 3, and we can bring that 1/2 down in front of the logarithm and rewrite this as 1/2 times the natural log of x squared plus 2x minus 3. And that way, when we find the derivative, the 1/2 is now just a constant multiple. So we can just bring it down and multiply it times the derivative of natural log of x squared plus 2x minus 3. And so remember, that's going to start as 1 over x squared plus 2x minus 3 times the derivative of x squared plus 2x minus 3, which is 2x plus 2. Okay, now, as far as simplifying goes, I'm noticing I may just start by multiplying straight across, you know, just to kind of condense this thing. We'll end up with 2x plus 2 over 2 times x squared plus 2x minus 3. But you guys notice, we can factor a 2 out of the numerator. And that way, it will simplify with the 2 in the denominator. So we can actually get this down to just x plus 1 over x squared plus 2x minus 3. Now, if, let's say, we could factor the x squared plus 2x minus 3, if one of those factors was x plus 1, I would definitely do that because then it would cancel with the x plus 1 in the numerator. But x squared plus 2x minus 3 actually factors into x plus 3 times x minus 1. So since nothing's going to cancel out, I'd probably just stop right there. Okay. Let's look at example 14. Okay, so here, y equals the natural log of x squared divided by 3x minus 2. So we can actually use this second property to expand and rewrite this as the natural log of x squared minus the natural log of 3x minus 2. Okay? And then that makes the derivative a lot easier because we can just find the derivative of each term. So derivative of natural log of x squared. Now that's going to be initially 1 over x squared times the derivative of x squared, which is 2x. Minus, okay, and then find the derivative of natural log of 3x minus 2. That'll be 1 over 3x minus 2 times the derivative of 3x minus 2, which is 3. Multiply straight across, we get 2x over x squared minus 3 over 3x minus 2. And then just a little simplifying, the x over x squared, simplifies to just 2 over x minus 3 over x, 3x minus 2. I'd probably just stop right there because to go further, we'd have to find a common denominator, all that good stuff. So we're just going to stop right there. All right, you guys, so this actually wraps up our derivative rules. So hopefully that makes you happy. And we'll definitely practice this in class. As always, thank you for watching and have a good night.